The second school of thought is the central engine hypothesis. The idea is the star collapsed, it formed a remnant inside of this expanding stellar carcass. And that remnant is putting out a ton of energy. The main theory that's sort of become mainstream is that the remnant is this thing called a magnetar. It's a neutron star with an extremely powerful magnetic field, spinning super rapidly. So to give you some perspective, the magnetic field of a magnetar is 100 trillion times stronger than that of the Earth's. Yeah, so, I hear people say stuff like, if you had a magnetar at the distance of the moon, it would wipe all the credit cards on Earth. I could do more than that. Like,
strip the iron out your blood.
Yeah, exactly. wipe out all life.
Yeah.
And then it's also spinning really fast. So this is an object with the mass of the sun in the size of the city we're in right now, Cambridge, spinning once every 4 milliseconds.
Okay, welcome to a new episode of Astronomers Meet the Astronomer, and it's a somewhat wonderful experience for me to invite Joseph here, and you're all thinking, Joseph is part of Astroveo, so what the heck is going on? However, there is a good reason why we're doing this. Joseph has recently defended his PhD.
Where there are neutrinos detected from the supernova. Kilpatrick et al. 123 were only able to place upper limits. They found no detections, and so they not let them place some constraints on whether or not there was some presence of a jet in it.
We expect neutrinos from a supernova to be detected from this far away.
A couple of weeks ago, I can't remember the date.
May 19th.
May 19th, thank you. Oh my gosh, that's a month ago.
I know exactly 1 month.
Holy schmoly. Yeah. And then I went out to Santa Barbara and celebrated with you. That was really nice. Thank you. I really enjoyed that.
Thank you for coming out.
You're very welcome.
I was incredibly grateful to have you out there.
Well, thank you. It was a long walk. But it's like 3,000 miles, you know. And also, you have recently had a professional development, which I think is exciting, and it merits completely this Meet the Astronomers being focused on you.
Thank you.
So you're very welcome. Congratulations on your PhD.
Thank you.
So I tell for my children, hello Benjamin, Charlotte, Tennessee, and Morris, they know me as Mr. Joseph. Well, now you're Dr. Joseph.
Yes. It's okay, my friends call me Mr. Joseph.
Okay, well, yeah, they should. Keep you humble. Keep you humble.
Exactly.
Tell us about your new professional development, please.
Well, so there's a couple things. We had a very exciting result published in Nature about a superluminous supernova. Mm-hmm. After I defended my PhD, I'm going to be in Boston, where we are now, for a couple months at the Black Hole Initiative, which is where we are today. And after I conclude the summer out here, I will be at Berkeley for the next 3 years.
Woo, baby! That's really exciting. Congratulations. You brushed over that very quickly. We are sitting in the Black Hole Initiative of Harvard University right now. We're, is it Garden Street we're on?
This is on Garden Street.
Garden Street, yes. And I used to work with Joseph on the Black Hole, the Event Horizon Telescope.
That's how we met.
In this very building, yes.
Yeah. Actually, the very day we met was in this building.
I know. Yeah. Seated around this table, I suspect, or these tables.
When I got here kind of late at night in the middle of an observation.
That's right.
David let me in because I didn't have card access yet, and then I was really nervous because I was an undergrad at the time and I was surrounded by some of the most brilliant people in the world, David included. And then David proceeded to sprint up the stairs 3 at a time, and I knew I'd come home. I had found my people.
That's right. Like, God, why didn't he take them 2 at a time? 3. Excuse me. Well, I remember that night, that very night actually. In fact, we were in an office just around the corner.
Yep.
And we were monitoring all these radio telescopes scattered around the world. And
yes, we were.
Making weather predictions and, what's the transparency of the night. And that was very interesting.
I was very Star Trek.
Yes, well, we were very glad to have you. And of course, now you're one of the superstars of the Event Horizon Telescope. And you've published many papers for us, so thank you for that.
Thank you.
Yeah. So, was it 1, 2 papers? No,
yeah.
No, you've published many papers. So this is, you know what? When we do these Meet the Astronomers, because of course you edit them for us, one of the things I have my list here is, I should not do this, although we did a little bit. Please introduce yourself.
My name is Dr. Joseph Farah.
Dr. Joseph
I just
Farah.
wanted to say that because I'm excited.
You should be.
I am currently a Black Hole Explorer postdoctoral fellow at the Black Hole Initiative. And in the fall, I'll be a Miller Fellow of Astrophysics at the Miller Institute for Basic Science at Berkeley.
Ooh, that's exciting. The Miller Fellowship is, and I know we discussed this, you didn't particularly want me to say this, but it is very prestigious. It's a fellowship across all disciplines, and you sort of won it / you earned it. And it is prestigious, and there are many thousands of applicants actually, and so you did a tremendous job, and I'm very proud of you, and I think it's going to be wonderful for you.
Thanks, David. It's across all science.
That's what I meant, all science disciplines.
I don't know if I don't think there are thousands of applicants because there's you have to be nominated by a senior someone, so there's like an initial cut. I don't know how many people.
So there were 3 applicants as well.
Exactly. Actually, it was just me.
That's right.
And I almost didn't get it.
You're the only applicant. Oh my gosh. Well, they have elections like that where only one person runs.
Yes.
You're guaranteed to get it.
I think I heard about a small town in some state where they're like right now they're having an election for mayor and like nobody is running. There's like no one's in there.
That's not a good sign. Now, I think I do know the answer for this, but for our 3 viewers, who are shortly going to be 2 viewers.
Well, it's 3 because now I'm in the video.
Well, that's true.
There's only 2.
Oh, my God.
We're down to 2.
So it's my mother and your mother, basically.
Exactly, yeah.
Where did you grow up?
So actually, well, I was born in Florida. I am
really?
technically a Florida man.
Oh, we didn't know
Yes, I know, but it explains some things, right?
Yes, it does.
But my family moved to Boston when I was really young, like maybe 2 years old. And I grew up there my whole life, did my K through 12, and got my bachelor's right in Boston.
Yeah, you were at BU, weren't you?
I was at UMass Boston.
UMass Boston.
Yeah, BU was I think right up the road.
Oh,
Or
so
maybe it
why-
was BC.
Why did I think you were Boston University?
Well, I mean, my alma mater has university and Boston in it.
So I'm just getting confused, basically.
I think so, yeah.
Right, okay. It happens very easily. Just so you know. In case you're wondering why I'm looking so red at the moment, I was at the beach on
He's
Friday.
embarrassed because of. He just gets flustered around me.
I mean greatness, in the presence of greatness.
Truly.
That's not it. It's definitely not. Well, no, you are a phenomenal
No.
scientist.
I'm not blisteringly phenomenal. So.
Yet.
Yeah. Yes.
Yet.
So someday maybe.
Yeah, so I went to the beach on Friday and I've got sort of sun-kissed, and I've been refereeing soccer this weekend, so I can feel it. My bed's touched by the sun. So, anyway, how did you become interested in astronomy?
Well, I was indoctrinated very young. My oldest or youngest formative memory was watching an episode of Nova called Welcome to Mars. Yeah, my parents were very big about science. Every Wednesday night, 9 p.m. Eastern, 8 p.m. Central, they would sit me down. Not sit me down, but we'd watch Nova together. And Nova was this amazing television program on
Was
PBS.
it super?
Yes, it was pretty.
You just got that joke.
Yeah.
It's such a bad joke.
Such a bad joke.
It really was.
Oh my god. They'd put us in front of the TV and we'd watch Nova and Nova's this general science and some history program. And literally the earliest memory I have was watching Welcome to Mars, which was this episode that came out in 2005, where they talked about the Spirit and Opportunity rovers and the kind of difficulties they had with them and all the exciting science they were going to do. And I can trace the feeling I have doing science and astrophysics back to that feeling I had watching that, and the feeling I still get when I watch that particular episode of like the pioneering spirit.
What was it called again?
It's called Welcome to Mars. It is fabulous.
I'm gonna have to look that
It's
up.
so good. It's like 240p, but it's so good.
Very nice. That's so funny.
It's really good.
What grabbed your attention about Mars in particular?
They ran into many problems, and they had to fix these problems, however far away Mars is. What is it like? Something about the problems they were having and having to fix them so remotely really made me feel like, oh my god, this is like so extreme. And the questions they were trying to answer about life and whether or not it can exist somewhere elsewhere on Earth. It's like these big questions, and it's like, oh my God, you get to think about that as a scientist? Like, people pay you to think about that?
Right. Not a lot.
Yeah, but I would do it for free.
Oh, yeah.
I would pay to do this.
Yeah.
And so it was something about that. It's always that, for me, that like the remoteness of it, whether it's, with supernova stuff, you just have a pixel of light that's getting brighter and dimmer, or it's, you're talking to a rover, millions of miles away. There's just something about it that
That's
gets
exciting.
me. Yeah.
I agree. I couldn't agree more. Would you go to Mars yourself?
Probably not. I don't think so.
Any particular reason?
I've seen pictures of it.
No. You've seen pictures of the Great Pyramid of Giza, but you still want to see the pyramids. So pictures good enough for you? That's not true.
I know, I'm kidding. I don't think I would go to Mars, to be honest. It kind of depends. Like, if it was like, would you go to Mars the way you'd go to Yosemite National Park? It's like, absolutely. But if it's like, when you say would you go to Mars, I immediately think there's like you have to be there for life, and you might be one of only a couple people.
That's true.
It's a one-way trip. Like, can I bring my wife?
Well, also, yes, true. But it depends on who's in the capsule with you.
Yes.
Can you bring your astro puppy? That's right. Yeah.
So, yeah.
Yeah. So could you bring your wife? Could you bring your dog?
Yeah. And he doesn't like, he doesn't like it when it's colder than 65 degrees outside and warmer than 75. So he might have a problem with the temperature and oxygen content.
As opposed to the 5G and the launch vehicle.
Yeah, exactly. No, I'm sure he'll be fine with that. He's got his dachshund, so he's got like a very big chest.
That's true.
He'll be fine.
Yeah. That's a lot of dog food to carry to Mars, by the way.
It is. Well, he's really small. I mean, they're small.
That's true.
He's a little dog.
Well, that's the problem. It's a 6 month journey.
Yeah.
And so, but I think the problem is getting back, because then you have to wait for, here's the Earth. You have to wait for Mars and the Earth then to get back in sync.
I think I would do that, though, if it was a return trip. That's like on a reasonable time scale.
Yeah, but the time scale, I think, is 5-7 years.
Even at the 5-year time scale, I might consider. Oh. But if it's like a lifetime thing where you can't get back, I'm not so sure. Would you do it?
That's a good question, especially as my children are a bit older now. I don't know. I think I always wanted to be an astronaut, and obviously wanted to do astrophysics.
Sorry, is the implication that when your children were younger, you would have yeeted out of here?
Funny you say that. It's Father's Day here in the US. I went out for...
Yes, happy Father's Day.
Thank you, I appreciate you. Happy Father's Day to your father, who's a wonderful human being.
He's amazing.
He is, he really is.
A big part of why I got into science.
No, absolutely. No, he's a fabulous man. But yeah, would I do that? I don't know. But again, the isolation of it, I think, is an interesting question about whether you could do the Robinson Crusoe type thing.
Yes.
But if you were in a capsule, again, with 2 or 3 other people, what happens if you didn't get along with them? Now, I could do it with you.
I think you'd be selected like NASA does for good personality compatibility.
Well,
right?
It's funny you say that. They do tests on Mauna Loa. They've got that, I can't remember.
The facility, right?
Yes.
Yeah.
And you go in there for I think it is 6 months at a time, and they see if you can live almost in isolation with 4 or 5 other people. And they're not allowed outside it's not a geodome, but it's I can't remember the name of it.
I saw that. They recently came back out a couple months ago, right?
That's right.
Yeah.
But there's definitely tensions in there because you're with the same 3 or 4 people for months.
Yes. No, I'm finding this interview even a little cloying, David. So.
Oh, yeah. But we've been together for like 6 hours. But so could I go to Mars with you, for instance? I think the answer is definitely
yes.
yes.
100%.
Yes.
Yeah.
Now, if we brought a chessboard, which I can see over there, I probably wouldn't because you'd beat me every single day.
That's not true. David's a very good chess player.
No, not compared to you. But so I think with the right person, and if you didn't have loved ones back on Earth. With your wife and my children and so on. I think that and our parents are still alive. So
I would not want to. Yeah, I want to see my parents more, not less. Right?
Yeah, that's right, absolutely. So I think that's a tough question.
Yeah.
And also for us, who are the type of scientists we are, we're not particularly planetary scientists. We're not astrobiology scientists. So would it be as interesting as doing some of the black hole science we do, or the stellar evolution research?
We could man a Mars-Earth VLBI baseline.
Oh, it's exciting. Very exciting. You do know that these capsules can't take that much hardware with them, right?
We'd build it.
We build it.
Yes, from the living rock.
From the living room. So basically you're going to MacGyver a radio telescope.
Exactly.
I
That was
love
my favorite episode.
Hey, that'd make a great new Nova episode. How to build a radio telescope on Mars.
With nothing but gum and what I have in my pockets.
Well, given the lack of water vapor in the atmosphere, you'd get amazing sensitivity.
It would be pretty good, yeah.
Oh my God.
And yeah, it would be pretty good.
Yeah,
you wouldn't have to worry about. You can go to really high frequencies.
And you'd get the baseline would be tens of millions of miles.
Yeah, and you could build a huge dish because you don't have to worry about zoning laws.
That's true too. Where are we getting electricity from? A really big solar sail, or like a massive solar panel?
I think it has to be a lot of solar panels.
Yeah, like hundreds of them.
Do radio telescopes use that much electricity? Like more than other astronomy?
Well, but you're moving hundreds of tons of metal, so typically.
For the
to physically move them in altars,
yeah,
you do need enormous current draws to move them.
That's a good point.
So yeah, that's probably one of the limiting factors.
We just push it.
What?
We're pretty strong.
Yeah. Well, the gravity is a lot less out there, but
That is
obviously.
true. Yeah.
But then all the dust would get in the gears.
I have asthma. That one.
Well, I'm not sitting in a capsule for 6 months with you coughing all the time.
This comment is going to come back to bite you when you cough 8 times during this interview.
I know.
He's got a little tickle.
I know. I do.
You want to cough right now, don't you?
That was psychosomatic.
That was, yeah. I played you like a fiddle.
You did. There was a great Blackadder episode in this is a BBC series in the 80s and early 90s, and it's just a comic genius, and the writing was unbelievable. And there was an episode, I think it was season 2, and Blackadder was getting married, and he chose this a best man, and the best man was this sort of super flash guy called Lord Flashheart, who was this sort of stud and a playboy, and he was just a funny character. Well, he didn't show up for a while, and so they were looking for a new best man, and the sort of stooge in the show was just this sort of like this very prattish and idiotic type person. And so Blackadder started looking around and was, who can I have as best man? And this guy, the guy who's going to do it, is like, yes, Percy, have you got something to say? I said, nothing, just clearing my throat. He says, good, I don't want you coughing all the way through this. Just hilarious.
That's so good.
Oh gosh. Well, just in case you want to know how it ends, Lord Flashheart does turn up. So
He does.
He does.
Okay.
He turns
Thank
up. It's just a bit
goodness.
late.
I was really worried about that.
You
actually.
were you? No. So we did the How Are You Interested in Astronomy. I do love that.
It's true. It's a true story. I wrote about it in my thesis acknowledgement.
I know. Is that the same thesis acknowledgement where I was mentioned like 2 or 3 words?
That's your name is only 2 words long. David James, the esteemed.
Yeah, thanks, David. Yeah. Well, if I was writing my thesis tomorrow, you'd get a whole paragraph. Just
Well, thank you. I appreciate it. I truthfully, I had difficulty trying to figure out where to put him. Like I consider him like a family member, like a brother, and but also he's an incredible friend and mentor.
Aww,
I eventually decided to put him in the mentor category. But it was very tough to figure out where to put you.
Just put right at the end.
Yeah, honestly, you should have just been in the title.
I like that.
And based on the number of questions, you should have been on the committee list.
Were your committee upset that I asked so many questions?
No, I don't think they were. They didn't mention anything. No.
I mean, it's like
I was really glad you did it because I felt more like I earned it after. I mean, my committee asked really good questions too, but like you really like made me work for it, and I'm grateful for that.
Well, I wasn't trying to be mean. I was very
No, you
interested.
weren't. You were just,
It was good science.
Yeah.
You did some
Thank you.
nice
That
work.
was, he asked for my thesis a week beforehand to come up with some questions.
Well, I didn't want to look foolish in case and said, "Hey, David, what did you think?" Like, I don't know. I didn't read it. I thought it just looked stupid. Okay, so we did that one. So how? Well, I think I know the answer to this, but our 2 viewers can find out. How did you become a professional astronomer/educator?
Well, I certainly wouldn't call myself an educator and sitting next to you,
Well,
which is one of the greatest teachers of our time.
Wow, we didn't go that far, but thank you.
So I kind of always wanted to. I always wanted to do science. I didn't know if I wasn't always sure I'd go into astronomy. Got really interested in physics and then astrophysics. I heard the call.
What would you have not done had you not done astrophysics?
I was gonna be a marine biologist when I was in middle school.
Wow.
Yeah. But
You'd have had a whale of a time.
I would have had a whale of a time. And then I went on a whale watch.
Did
and
you really?
found out that I get seasick extremely easily.
God.
And the dream died there.
So you'd be there with Jacques Cousteau, like, oh, sorry.
Yes. Yeah. I also I was trying to learn about how do you become a marine biologist. And I read a story from someone who basically said that, like, there's like a lot of people think it's like very glamorous of like, you're like swimming among the sharks and like having, doing tests in like a beautiful coral reef or something. He's like, what I actually did was like I sat out the back of a seafood restaurant and like counted the eggs in fish that they were throwing out. And I was like, that sounds very unappealing.
Yeah.
All fields kind of have that. Like I think in astronomy, you might hear what we do and think like, oh, you were like looking through a telescope on like a cold winter's night, like, taking data, like, oh my God, a supernova just went off. And really it's like mostly just staring at code and a lot of math and histograms.
Well, that's true. Let me interrupt you there briefly because I used a telescope in South Africa. This was about 25 years ago, and it was a small aperture, it was 50 centimeters, so really quite a small telescope. And it was an old-fashioned telescope. I can't remember when it was built, but it was built like in something like 1936 or something. And it didn't have an electric drive. It had setting circles, so you slewed to your star or galaxy, whatever you were observing, and observed it by basically moving the telescope.
Wow, like a Dob.
With crayons, like a Dob, like a Dobsonian. Excuse me, there's that cough.
That's number 2.
Darn it. How many am I on? 7? 8.
You have 6 remaining.
6 remaining, okay, thank you. I'm going to write that down. And it was the middle of winter, so maybe July, August in South Africa. And I was doing some work with Louis Bologna, some BE star work, and we were observing BE stars and we were measuring their fluctuations to see if
That's what you did your PhD thesis on, right?
No, I actually did stellar evolution. So I did rotation X-rays and lithium evolution.
Right,
stellar
lithium.
cluster.
Yep, sorry.
But I sort of branched out a little bit, and so I used to look at angular momentum evolution of stars, and of course all stars slow down, and sun-like stars slow down by throwing off, they throw off almost like the solar wind. Well, that slows the sun down because the ionized plasma is anchored to the magnetic field. You get frame dragging, and the magnetic field is anchored to the surface, and it slows down.
Is that frame dragging?
Well, not frame dragging in the relativistic sense.
You mean it co-rotates with the magnetic field?
Yeah, but
that's flux freezing, right?
Yeah, like flux freezing.
Okay,
That's exactly it. I used the wrong term. And so it retards the rotation rate of the star. It takes millions of years to do this, of course, hundreds of millions of years. But of course that evolves to things like coronal mass ejections and so on. And so late type stars typically emit these clouds of material, and we detect them with H-alpha, the Balmer series of H-alpha. So I got into BE stars, which are hot stars, typically 20,000 degrees-ish or more, and the E stands for Balmer series emission. So I was working with Louis to look at the photometric variations of these stars. So what we would do, and this was in I think it was near infrared. Was it near infrared? No, it was actually maybe in the blue band. So we put these filters in, but what you do is you do star, sky, star, sky, star, sky, and it had a photomultiplier. And so you do 30 seconds, measure the flux, sky, so background subtract. Well, you had to line the star up every time, and so I'd climb up this ladder, look through the eyepiece, and it was middle of winter, so the eyepiece was blinking, freezing, but you'd have to put your eye against it to line the star up. And the ladder was maybe 7-8 feet. So all night, every 30 seconds, I was up and down that ladder with my eye against this freezing eyepiece. That was not glamorous astronomy, let me tell you. Oh my gosh, it was awful.
But that sounds closer to like the romantic idea of astronomy people have, because you're like legit. We're in like the big data and robotics era of astronomy now. So like my PhD was on an amazing robotic telescope called Les Combres Observatory. So you're much closer to like you're a legit astronomer. I'm like a facsimile.
No, you just do everything with. You're much better at coding than me. I was much better at.
You're very good at observations.
Yeah, I'm pretty decent at observations, but you're obviously a much better coder.
No, but you're very good yourself. So.
Well, I don't know about that. So anyway, I completely sidetracked you with your biological thing there.
Oh yeah.
So you found yourself being seasick?
Yes. And so I was like, I cast around for a new science, and my mom at some, growing up, my mom and dad, like, whenever we had the time and like money, we'd try to go to the Museum of Science and
That's a great
the aquarium.
museum,
It's amazing. I volunteered there for a little bit.
Oh, did you?
I did, yeah. She would give me these books every now and then, and almost all of them I still have. But I remember in middle school she got me Hyperspace by Michio Kaku, and I was like, oh my god, theoretical physics is like awesome. And I bought like 4 more of his books and like read them, and I was like, for a while I was like on the theoretical physics train, and my first significant research experience was in particle physics with Melissa Franklin, who was sort of my first long-term research advisor, and she is an absolute legend. And I'm very grateful to.
This was undergrad?
This is I worked with her. It was right after high school.
Oh, yeah.
I started working before I started undergrad, but then I worked with her for about maybe 8 months. We did a lot of particle physics, and I was definitely starting to lean more towards the astrophysics side. And then so after I finished with a group, she helped me get a job with the Event Horizon Telescope, and that was how I got sort of hooked on radio astronomy, which is awesome.
Yeah, you did a summer internship with us, didn't you? Is that how you started?
It was. I was with the guys for like 4 years.
Yeah, but that's how. But
how I started.
that's how you started.
Yeah, I mean, it was.
Was that a summer internship?
It was.
Or was it during the year?
It was. I mean, I started in May. I talked to Michael in March 2018, and I started observing with you guys April. The observation.
That's
campaign,
true.
right?
You're right. You're right.
It was before the summer.
It was April. You're right.
Yeah.
Yeah, because I became program manager of the Event Horizon Telescope in November 2017.
Yeah. So we were like right.
Almost contemporaneous.
Yeah. Which is pretty cool.
Congratulations! Welcome to the Event Horizon Telescope.
So finally, I've been waiting for decades.
Nobody's talked to me for 10 years.
We've known each other almost 10 years.
Oh, I guess that's true. What, 8 years? Yeah, that's amazing.
Yeah, that's.
Can you believe that?
I can't.
I knew you as a boy.
I was. Now I am a boy-sized man.
A boy-sized man with a PhD.
With a PhD.
Yeah. I really enjoyed those early years, actually. I have to say.
That was so much fun. It was very intimidating being in the Event Horizon Telescope. You're surrounded by some of the smartest people like ever, and everyone was super nice. But like David just makes everybody. You just make everybody feel welcome.
I appreciate that. Thank you.
And you were a wonderful mentor to me.
Well, thank you. You were a great friend to me too.
And that's when we started Astroveo.
That's when we started Astro. We were doing the color images.
Right up the street from here. Yeah.
I know. That's when we started.
We were at an art company.
Yeah. I would like to get back into that.
I would
eventually,
like
actually.
to. Yes.
I love
that.
those.
Was fun.
It was.
And it came out really good.
Yeah. Well, we've got hundreds of color images, so we should think about that. But we talked about this on the way over, actually, and it's one of those things that the Event Horizon Telescope is this 300-person-ish collaboration, and it's made up of some incredibly talented people.
Oh yes.
And people like myself and you, and probably everybody in the collaboration, we probably were very good in high school, top of the class at undergrad, and then by the time you get into someone like the Event Horizon Telescope, you realise that while you're still one of the sort of more sort of elite performers, everybody else is as well.
I mean, I think it's just sort of generally true for like if you're doing a PhD program in anything, you're going to be surrounded by very talented, true. Super smart people.
Yeah.
It's the best part about being in academia. Like everyone here is brilliant.
Yeah.
I learn so much every day. I don't know how much I would get of that elsewhere.
Yeah. Well, it's a complete privilege, actually.
It is. Yeah.
A complete privilege that we have the opportunity to do that.
David saying that's a complete privilege is a big thing. When he says that, he means it.
I do.
The last time you said those words exactly was when you were standing on top of Cerro Tololo, looking out on an incredible sunset. So,
oh, really? In one of our videos?
In the above the
clouds, yeah. The sort of sheer joy that I have from coming to use these instruments. I told my mother, all those times you bought me books and telescopes when I was a kid, paid off, because I get to come to places like this. It's completely privileged. Well, I often thought about that, I'm a sort of boy from a small town in Wales, but, there are people who just don't have the opportunity. There may be many wonderful scientists out there who never get the chance to do what we do.
We are the luckiest people.
Absolutely. We do what we love, and as you say, we're sort of fortunate to be paid for it. But there are many people who just never have either the opportunity or the means, or they have to go out to work to help support the family, or certain countries, so certain demographics just aren't allowed to be educated. We're phenomenally lucky.
We are.
And let's face it, we also won the genetic lottery that we have brains that just understand mathematics reasonably well. And
You did. I generally don't feel like a lot of this stuff comes to me easily. I have friends that are really, really good at math, including yourself, and it's something I have to work at and get better. So I feel very grateful that I have had the support that I have in order to get good at the things I need to get good at to participate in these amazing discoveries, and it's always a learning experience.
it is. That's a great way. Actually, you said a really important thing there. We've had a lot of support, obviously with your family, but your mentors that you've had, the teams you've joined. We're not a one-person band by any stretch.
I am constantly aware that this wild dream I have is being held aloft by 1,000 hands, and I'm very grateful for that.
Yeah,
for
absolutely.
every one of them.
That's a great way of putting it. Yeah, we are completely privileged. Knowing what you know now, if you won the lottery tomorrow, you had sort of independent means, would you still be an astronomer?
In this economy?
Well, you'd have enough money to beat the economy, right?
I know 100% I would still be a scientist.
Yeah.
I love astronomy and I love astrophysics. I'm not saying I don't know because I don't enjoy what I do. I deeply enjoy what I do. With no constraint of budget, I wonder if I would maybe start feeling the pull to think about riskier problems, like more on like the quantum gravity end, or the bigger like cosmology stuff. But I probably would still do astrophysics. Yeah. I would do what Wayne Rosing did and use my to found an observatory.
Robotics network around the globe.
Which is, one of the biggest contributions to science ever. I think.
Absolutely. Yeah, no, he's an amazing philanthropist. Amazing. Yeah, I definitely would, but I think I would fund institutes for people of excellence.
Ooh, the David James Chair of.
No, I don't have to. I don't have to have my name on it. And
I would put your name on it.
Well, in small letters maybe, but
small caps.
Very small caps, yeah. But I think I would also have a stream for the K through 12, so funding for underprivileged kids to sort of have a chance to become scientists.
Yes.
And then maybe a sort of a really big pot. So someone like you could say, I don't want a 15-page proposal. Right. First of all, I'm not sure I want to read that much anymore. But I'd say or maybe a video call. Tell me why I should give you $5 million for the next 3 years to study supernovae or event horizon telescope black hole theory. In a video call, just tell me, excite me. And then I'd say, okay, I believe in your project, here's $5 million, go and do your research, publish and mentor people the best you can, and we'll talk again in 5 years' time.
Aren't you worried that by doing that though, you select for the people that are able to convince you of things as opposed to and sell you on big things instead of people that have a balance between the big questions and being able to get it done? Because I could walk in and sell you on the I sell you on the n=5 photon ring, but not have any hope of detecting it.
Yes. Well, while I do definitely look fairly stupid, I think I'm well enough read in astrophysics that I could decide what is viable and what isn't.
You do not look stupid. You do not look stupid. My concern would be more on the things on the edge of viability. I've been learning a lot about Fisher matrices for a paper that I'm writing right now, and it is very easy to convince yourself that you can do a lot more than you can in reality because of if there was a thing like that, I would want you to be the person to be figuring out what's good and what isn't. Because I think you're exactly right. You're really good at that. You have a great nose for that stuff, and you know a lot, and you're a perfect person for that.
Well, I appreciate that.
I mean, I don't know if you guys know, but like David has touched almost every aspect of astrophysics. You can find it. You pick literally any subfield, and he's almost certainly got a paper with his name on it in there.
That might be true.
Which I think is actually true. You have one of the most eye-watering careers I have ever seen in terms of.
I've been very lucky.
Yeah.
I have been lucky. I do like what you said though. So I think if let's say you had a pot of let's say $1 billion, for instance. So I think what you could do is put 5% into high-risk projects, maybe 70% into mainstream projects with high value and are just interesting.
And 25% Lamborghinis.
Yes, that's right. Every researcher gets a Lamborghini or Aston Martin. But I think
Or 1 month's rent.
Yeah, in this city, that's about right. But what you could then do is maybe fund, again, people who do great mentorship, for instance, and so can bring, again, junior scientists through and early career scientists. So I think you could have a really broad portfolio, and you would allow yourself to have some level of funding for the riskier projects, that if they fail, but you learn a lot in...
It's a venture capital approach.
Almost,
Yeah.
but if you've got almost unlimited wealth, or you've got $1 billion and you don't mind losing that, then why not take some risks? You might learn some great things. Your mainstream science still gets done, and then the early career scientist portfolio is sort of helping sort of mentor the next generation.
I like that. I like that a lot.
I think that's what I'd like to do.
Yeah.
But I don't know. I'd just like to have $1 billion.
I would like the $5 million, please. Yeah, please and thank you.
Gotta convince me. I'd probably just say yeah.
Just circular financing.
That's right. Well, it does beg the question of, and you see this in the funding agencies, there is definitely a budget for people doing sort of more exciting, sort of sexy, quote unquote, science, but you still need an awful large pot for the people doing just interesting astrophysics, because it bleeds into so many other areas of science.
And you need the less flashy stuff that pushes the field forward. I mean,
Absolutely.
That's what it's all science is built on. Incremental progress.
Incremental progress. 100% right. We all stand on the shoulders of giants.
We do. I mean, metaphorically.
I'm tall.
Yeah.
I got that reference. They can't tell us I'm sitting down.
Yeah.
I'm 6'4", so he's making a nice joke there. Okay, we spent a lot of time on that, but I find that fascinating.
I do too.
Actually.
Yeah, it's a very interesting question.
I love. I want to go back to the marine biology thing, because I don't know if you've ever read this book. I suspect you have, but I always loved 20,000 Leagues Under the Sea by Jules Verne.
Fantastic book.
I mean, amazing visionary, much like H.G. Wells was, in fact. And I'm rereading War of the Worlds right now.
Oh, it's amazing. You know the story about the radio?
Oh, 1913.
1913, yeah, when people thought it was real.
Yeah. It was I think it was 1936 or 30.
I think it was 30. It was like the early 1900s.
Yeah. Was it Orson Welles, I think, that did it?
I'm not sure, but it was that
was terrifying, that radio. I actually listened to it when I was about 20.
They knew what they were doing.
Oh, yeah. It was
that was not an accident.
No, it was horrendous. But like I said, I'm rereading the book. I've read it before, but it's actually quite a scary book.
Yeah, it's pretty scary, yeah.
Yeah. Especially for in that epoch, so you're talking like late 1800s.
Yeah.
The science literacy of the general population was probably low enough that they couldn't really tell fact from fiction.
Yeah.
It's a scary book.
I think it's scarier than a lot of the stuff made today, where it's like, so much of science fiction now is like bureaucracy for some reason, and there's a place for that. Like, I love Star Trek and Star Wars as much as anybody.
Oh yeah.
But there's something raw about War of the Worlds. It makes you feel like just a bunch of like apes that got visited by, like, you know what I mean? That's what it makes you feel like. It makes you feel like we are helpless.
Yeah, but it almost puts humans in their place.
Yes. Yeah.
In fact, it references that in there about how did Martians or the purported Martians, did they see us as we see the base animals?
Yes. Yeah.
It actually references that.
It's like, it makes you think like, we don't treat animals that well.
No, we don't.
Why would we expect to be treated?
Absolutely.
Whatever species that treats
absolutely.
them?
Yeah, it's very humbling. But the 20,000 Leagues Under the Sea, I absolutely adored that book.
It was so good, yeah.
Amazing.
Any of Jules Verne stuff.
Yeah,
Like,
the
one around the world.
Around the World in 80
I just haven't read that one in a while, but it's so
amazing.
good.
Yeah, I read that in French actually, and I learned so much.
I can barely get through it in English.
Well, I learned a lot of my French vocabulary comes from reading books like that. And
Really?
It's just beautiful book, really, very nice, very nicely written. Okay, this is going to be one of the most interesting things for me, although I know a lot about you personally, of course. What is and are, so if it's multiple, of course it is, your main research fields?
So I work on compact objects, I would say.
What does that mean to our viewing public?
Black holes and neutron stars.
What does that mean to our viewing public?
So when a star dies, its core collapses in a humongous explosion, and that collapse forces protons and electrons together into neutrons, creating a neutron star, which
so it
is
literally is made of neutrons.
literally made of neutrons. But the star is exceeding nuclear saturation density, so it's made of neutrons. It's like a atomic nucleus the size of a city. Yeah, like they're even more densely packed. And in the mid, the outer layer of this star is like the hardest iron you can imagine, because it's from the dense iron that was in the star before it died. But then you get through the neutron layer, and then in the interior, the density is so high that you're past neutrons and particles are just blurring together, and you get some people think of quark gluon plasma.
Yeah, quark soup.
But the truth is, we don't know what's inside these things. We do know that if the density is high enough, so in the 1930s, Oppenheimer and Volkoff, I think, wrote the original paper calculating the upper limit of a neutron star, which they found it to be 0.7 solar masses, but that's actually wrong. Later we found out that it's closer to like 2, a little bit above 2. If you get above roughly 2 solar masses, then the star will collapse further into a black hole, which is an object that is so high density that, you know what? I've been saying high density, and that's not exactly true. It is an object with mass concentrated into a small enough region that light can escape. The reason I make this clarification on density is because you hear that and people say, oh, it's a very dense thing. And it's like, not necessarily. You can have lower density over a very large volume consistently. So like, if you wanted to make the sun into a black hole, you need to compress it into the size of a city, a small city. For the Earth, it would be a marble. That is very dense, right? That's a solar mass in the size of a couple kilometers. But for a supermassive black hole, the density drops with the size. So, M87's density, which is 6 billion times the mass of the sun, its density is lower than that of air on average. So that's why I kind of want to be careful with the word density. But
I always think of it as sort of like gravitational density over an extended field.
Yeah, it's about the curvature it generates.
Yes, right.
So we study black holes. I study black holes on horizon scales using radio astronomy, like David. And then for neutron stars, that's something I've gotten into more recently. And the venue via which I am interested in studying those is how their impact on supernovae when they form after the collapse of the star. So I worked on supernova a lot for my PhD, and very interested in how stars die, particularly because of the remnants they leave behind, which are these very powerful compact objects.
All right, so I ask this of all people, and in fact, it's one of the questions I like asking myself the most. Who cares?
Who cares? Yeah, that's a very fair question. There's black holes and neutron stars are the most extreme objects in the universe. So they test our most fundamental theories in regimes we cannot hope to reproduce on Earth. Right. And the reason you should care about that is because testing those theories is really important. The better we understand the universe, the more we can, frankly, bend it to our will. And
that is lovely.
So the quantum mechanics is one of the most fundamental theories we have, and the rush of understanding we got at the beginning of the 19th century led to developments from the transistors in the phone taking this video to the atomic bomb. And
20th century.
Oh, I'm so sorry, 20th century. I meant 1900s.
Yes,
Sorry. Yeah. So when we understand the universe better, we can do things with that. It's like increasing our power level in a video game. And we've gotten really good. Our theories are really good, but we know they're wrong. And that's really problematic, because when our theories are wrong, it means we're missing something. And there could be whole aspects of reality and existence and technology that we're not unlocking because we're wrong at some level about how the universe functions. So we need to figure out where we're wrong, why, and how to fix it. And the only way to do that is to test our theories where we know they will break down. And neutron stars and black holes are two of the best candidates to do that.
Yeah, it's very extreme astrophysics.
Very extreme. Extreme astrophysics was in my thesis title, actually.
Yes, indeed
Yeah.
so. Well, one thing I love about the Event Horizon Telescope project, and I'm part of another project, a collaboration called the DELVE collaboration, which was sort of spawned from the Dark Energy Survey, which I'm still a part of. We used the Dark Energy camera on the Blanco telescope at Cerro Tololo to photometrically map the sky. And one of the things we were doing, and we do with the DELVE collaboration, is we're essentially discovering and mapping the dwarf galaxies that orbit the Milky Way and some stellar streams. And essentially what we're doing is we're probing the gravitational potential of the Milky Way.
Extremely cool.
Which is actually a lovely project, but it's fundamentally to understand Einstein's field equations, which is a large part of what the Event Horizon Telescope is for. And then sometimes people say, well, that's really interesting and cool, but why? Well, even at the basic level for my mother or for your mother is GPS. Without Einstein's field corrections, time corrections to GPS satellites, you don't get the right answer as to where you are. And the finer those corrections, that's part of the reason how you can get better and better GPS locations on Earth. So there is an immediate effect of us doing this kind of research right now for humanity. And I realize it's sort of almost like a trivial one, and I agree with you about extreme astrophysics.
But it won't be trivial as we expand to the stars and beyond.
Absolutely.
Yeah.
Well, unfortunately, one of the best uses for it, depending on your definition of best, is for the military. They can fly missiles through windows in buildings halfway, a continent away, which I agree is a terrible use of our science. But that precision that the GPS corrections allow for that kind of sort of longitude, latitude precision on Earth, which is phenomenal when you think about it.
I agree. I have to confess that while I have gotten relatively adept at answering the why should we care question, and I try to appeal immediately to the practical usage, I don't care for that reason that much.
No.
I admit that the open questions in science are really scary, and they keep me up at night because they are asking questions about the fundamental nature of reality, and it bothers me that we don't have the answers. And I wish that was a good enough reason, and I think it should be a good enough reason for everyone.
I agree.
Because I think there's two types of people. There's people who think that the questions that are still open in science are really scary and important, and there's people who don't understand what those questions are.
Well, it's also people who just don't care.
I think that even people who don't care, if they did care, even if they understood exactly if they understood the questions we're grappling with, they would care. And I think that part of it falls on us, that we're not doing a good enough job communicating why.
Yeah, correct. I
and that's something that I want to get better at, is making people care for the reasons I care, not just the reasons I think they will care. You know what I mean?
Yes, but you have to do it in an unbiased way.
Yeah.
Because of course we've, as you and I discussed, we had a long conversation this evening about all sorts of other things. Humans are frail in terms of their own biases.
And that's what scientists as well.
Scientists as well.
And the whole scientific method is trying to get us to stop being biased.
Absolutely.
And we have to have a method because we're not good at it.
Well, I actually love that what you just said, because you, especially here in modern times and in the US in particular, there's all these statements about is climate change real and so on, or I don't believe it.
Yeah.
And the beauty of science is it can still be true even if you don't believe it. And it's founded upon 1 + 1 is 2 and 1 - 1 is 0. Everything, and some geometry of course, everything after that, if you start with that foundation, almost all science is built on truisms. So by the time you get to climate science, while you can debate its impact, as long as you've got good data, whether you believe it or not, it's still occurring.
I'm not sure I agree with you, David.
Tell me why.
Climate change is a hoax. Sorry, I'm kidding.
Okay, so we're going to cancel this episode and we're going to edit Joseph out.
That would probably be for the best. I actually don't think that's true. Thinking carefully about that, Math is built on axioms. And math is way more rigorous than science.
That's true.
And it's fundamentally built on axioms that are assumed, not proved. So at one level, I think that it's not entirely true that what we do is based on fundamental truisms. Because 1 + 1 = 2 is an axiom, not a truth. But there's a deeper reason that I disagree, which is if what you're saying was true, we would have solved everything just using math. And we can't. Because mathematical consistency is a necessary but not sufficient condition for reality. Reality is mathematically consistent, but there are many realities that are all mathematically consistent and we're not in them. That's the big issue, right? All the different theories of everything that have come up, they're all mathematically consistent, but we have no idea which ones describe our universe because we can't test them.
That sounds like string theory to me.
Yeah, I'm trying to, so science, I think, is what separates science from math is not that it's built upon truisms. It's about confronting self-consistent ideas with data.
I would accept that.
Yeah, I think it's because I think that if you argued for climate change on those grounds, like as in if you argued for the validity of climate science on those grounds, you could find mistakes in climate science or things that weren't done well or data that was not represented, data that was not accurate. Because that happens in all of science. Like even if you do all of science correctly, perfectly, something like 30% of published studies will be incorrect because the number of wrong hypotheses outnumber the number of correct ones.
Yes, but with good data, that should become less and less.
No, so if you there's a great Veritasium video. Derek, I forget what his last name is. But there's a great Veritasium video that kind of breaks this down, and he does this amazing thought experiment where he suggests that, let's say, I forget exactly what the numbers are, but it's something like, we produce way more wrong ideas than we do right ones. And so let's say we test a bunch, right? And you have like please don't quote me on the numbers because I don't remember, but let's say it's like a 1 to 20 ratio of wrong hypotheses to right ones. And if your experiments have 80% statistical power, that means 80% of the time they will correctly identify that the right idea was correct. And 20% of the time they'll incorrectly identify that they'll say the right idea was incorrect. The problem is though, if you assume a statistical significance for a p-value of let's say 0.05, you will have almost as many correct right ideas as studies that were wrong but looked statistically correct because they were a fluke. And if you, in the numbers he gave, which were honestly optimistic in my opinion, 30% straight off the bat, 30% of published literature will be unreproducible nonsense. Just even if everyone's doing everything perfectly right.
That's depressing.
No, but it's how science is. Science is never ever claimed to be perfect. And I think that people want to look to science as some sort of I believe in climate change. I believe in black holes. It's like, no. Science never asks for your belief, just your eyes and ears. But it's never claimed to be an all-knowing sort of deity that just tells you the right answer all the time. But
that's true.
It's the best. It's the best method we have
at the moment.
I think it will ever be.
Maybe.
It's the best we have, and it's still imperfect. And I think that we need to be honest about that, because if we say science is built on truisms, then how come science can be wrong, even when scientists are doing everything right? Was that too philosophical?
No, I like it. No, this is kind of discussions we should be having. Yeah, I need to think about that a fair bit more. I do. So of course, most of my career has been data driven.
Same.
Yeah, but I think you understand the theoretical side of astrophysics better than I do, and I think I've always wanted data to prove or disprove any theories I've had. But you're also right in that your theories one's theories are almost always incomplete, and sometimes just out and out wrong, of course. Which is, I think, a very healthy way for science to be.
Yeah.
Maybe you're right. Maybe we should be better about knowing the limitations of science and saying, well, even if your theories prove correct, it might not be the correct theory.
Yeah. And I very obviously, I'm not a science denier.
No. But you have a healthy skepticism about what we do and why we do it.
I think I think that my perspective is there is a distinction between data is the ultimate test, which is true. Data is the ultimate thing that matters. And also data and our data collection and our scientific method is imperfect. It results in the wrong answer a lot of the time.
Yeah. I wonder if we asked the right questions, whether it would.
No, even if you ask the question perfectly, you still can't beat the. It's because we're not good at coming up with the right idea.
Right.
There are just too many wrong ideas, and at a 5% statistical fluke rate, you're going to say the wrong ideas are right 5% of the time, and that's going to either be comparable to or outnumber the right ideas that get correctly shown to be right.
I wonder if that's a function of our limited intelligence and almost like the uncertainty principle, where there's just, you can't know everything precisely enough, even if you've got perfect data.
That's an interesting idea. I'm not sure. If we were more intelligent, if we maybe if we didn't experience the passage of time, maybe we would have a different perspective on the scientific method.
Well, of course, as all scientists are, we throw in a little bit of pride in there, and a bit of bias, and a bit of humanity.
It's true. And honestly, you and I, based on the lengths of our videos, do not experience the passage of time. So
I know. Well, I think if you were to do a time series, like, that guy's getting grayer and grayer and grayer, your beard is getting longer and longer.
This will be a 30-minute episode. 2 hours in.
Yeah. I think we're about an hour in. So, well, I love this. So let's move on. Well, I don't know. So in fact, on my list here, typically is ask the interviewee some questions about their science. So I think we've done that. I still think I would have one or two more questions for you.
Okay.
Especially as you had branched out from the Event Horizon Telescope to supernova science.
Uh-huh.
So tell us a little bit more about, although I think we have covered this in another episode, but I think it's so fascinating we should stay on it. These superluminous supernovae and the magnetar discovery that you had made, and obviously made a big splash in both scientific literature and in the press. Tell us about that. I mean, it was a phenomenal discovery.
Thank you. So there's supernovae, which are the explosive deaths of massive stars. And when a star dies, it releases enough energy to outshine an entire galaxy for a few weeks, which is insane.
Incredible.
That's great for us, because it means we can spot them across the universe. And the story of supernovae is really funny. Not funny, it's really interesting. We had a really hard time explaining them for a while because they require so much energy. And eventually we pulled out all the stops, pushed everything to the limit, and said, okay, we finally found enough energy to explain the supernovae we see. And then in the mid-2000s to 2010, actually my PhD advisor, Andy Howell, discovered that there are an entire type of supernovae that are 10 to 100 times brighter than regular supernovae. He called them superluminous supernovae. He likes naming things super.
Nothing wrong with that.
Oh, no problem. He has a software pipeline called SuperFit. He also discovered Super Chandrasekhar supernovae.
Oh.
So yep, he's big into this, and superluminous supernovae. So they did all this work and they confirmed that this thing is 10 to 100 times brighter than other supernovae, and they found many more of them after that. To date, we have roughly 300 Type 1 superluminous supernovae, I think is about the number.
300?
300, yeah. Wow. Out of 15,000 known supernovae, so they're really rare.
Yeah.
So now we're back at square one. You have to explain how something could be so bright. And there's a lot of theories of how this could happen. And there are many different ideas with varying degrees of plausibility. The most plausible, sort of the ones that won out in terms of plausibility, came down to two sort of schools of thought. The first was the shock wave that the supernova produces runs into material that was around the star before it died. This can be material that was around the star already, or stuff the star shed before it died. They are very unstable towards the end of their lives. And as a result, they will lose a lot of mass, and maybe there's a shock wave that runs into that stuff. And when it runs into it, heats it up and causes it to glow, and that will produce these bumpy light curves that are very bright, which is what we see. Because that's the other weird thing about superluminous supernovae. Most supernova light curves are just super smooth. They rise and they fall. But superluminous supernovae are very bumpy, kind of go up and down, like this.
Ooh.
Yeah. So most supernovae light curves, in terms of luminosity versus time, they'll rise smoothly and then fall. But then superluminous supernovae are 10 to 100 times brighter, and they'll have these weird bumps, and you have to explain them. So this idea, this is called circumstellar interaction, circumstellar interaction or CSM interaction, that's the idea. Shockwave runs into circumstellar material, you get extra bright, a lot of bumps. It has some problems. Sometimes we see superluminous supernovae with a lot of bumps. And that means you need many, many shells, and each of those shells has like 5 or 6 parameters you can play with. And so at some point you're just doing a series expansion in shells of CSM, and it's like, okay, are we really figuring out what's going on here, or are we just pattern matching?
Yeah.
The other problem is sometimes we see supernovae that don't have bumps at all, but they're still very bright. So why does that happen? So that's one school of thought. The second school of thought is the central engine hypothesis. The idea is the star collapsed, it formed a remnant inside of this expanding stellar carcass. And that remnant is putting out a ton of energy. The main theory that's sort of become mainstream is that the remnant is this thing called a magnetar. It's a neutron star with an extremely powerful magnetic field, spinning super rapidly. So to give you some perspective, the magnetic field of a magnetar is 100 trillion times stronger than that of the Earth's. Yeah, so, I hear people say stuff like, if you had a magnetar at the distance of the moon, it would wipe all the credit cards on Earth. I could do more than that. Like,
strip the iron out your blood.
Yeah, exactly. wipe out all life.
Yeah.
And then it's also spinning really fast. So this is an object with the mass of the sun in the size of the city we're in right now, Cambridge, spinning once every 4 milliseconds, or 1 to 30 milliseconds. So a ton of energy. And that energy gets deposited into the ejecta, which causes it to glow extra bright. The problem with the magnetar hypothesis is that you can't get bumps out of it natively. It's a very smooth power injection. So you have one theory that can explain almost every light curve you see, but it can't explain the minor features in the light curve. And then you have this other theory that can explain some of the light curves we see really well, but no. And the real problem with both of these is that we have no way to tell which one is right. So you can fit these models to the data, and they fit, but that's not a proof. You could fit the CSM interaction model to my heartbeat. That doesn't mean I have an expanding shockwave running into shells of matter inside me, although I could, but it doesn't rule it out. So
probably don't.
Right. So we didn't have any way to prove this. All we had was circumstantial evidence. And so what we've been on the lookout for is some sort of incontrovertible proof, like one of these mechanisms is happening in a way that cannot be explained by the other. And we just didn't have that for 16 years, ever since the sort of seminal magnetar theory paper came out. The idea was first proposed by Lars Bildston and Dan Kaysen, and independently by Stan Woosley. And we just didn't have sort of evidence of this. But then, in December 2024, we saw a supernova that had a really strange light curve. And the light curve had bumps in it, but the bumps were a perfect sinusoidal wave, and they were getting closer together. So whereas most sort of supernova light curves look really bumpy like this light curve that we were looking at from the supernova 2024 AFAV, it went up like this, and then it rang like a bell. And when you look at the residual versus time, it looked like this, like a perfect sinusoid, where, let me draw that a little bit better, sorry.
That's the world's biggest eraser.
I know, it's so big. It did this, where the distance between the bumps got smaller. Ooh, I look like I ate a bunch of Cheetos.
Yeah.
That's really, really, really hard to explain. And actually to the extent that we've never seen something like that before. So we called it a chirp because it looks like a gravitational wave chirp. Mm-hmm. And that functional form is what gave us the idea that there might be something related to infall or inspiraling inside of it. So we tried to explain it with the two theories, and both of them failed. in the sort of ways they usually do. With the magnetar model, it just goes through the bumps, it ignores them. With the CSM model, we saw like 4 confirmed bumps, possibly a 5th. You would need like 50 parameters. And then the light curve still doesn't work because CSM interaction can't easily explain a sinusoidal light curve. At least not the model we use. So we had to come up with something completely new. And this was the idea we had. You take a magnetar and you surround it with a disk, an accretion disk. And this is something that can happen in nature. Not all of the material that gets thrown off by the star gets completely ejected and gravitationally unbound. Some of it might fall back. And if there's a very gravitationally strong object there, it'll circularize around it and form a disk. And the cool thing about a disk is that if it's tilted, it can block light from along your line of sight. Now, what does that look like? It'll look like a dip in your light curve. If the disk is the other way, where it's sort of facing you, some of the light from the back of the magnetar will get reflected, and you'll get more light, so you'll get a peak. And if it's tilted, it will experience something called precession, which is when an object's axis of alignment rotates around some node, right? So if you've ever seen a spinning top, it will precess around its sort of around the top to bottom axis. And if this happens, the light will be periodically blocked in exactly a sine wave. It'll be blocked and reflected and blocked and reflected in a sine wave. Now, that explains the oscillations, but it doesn't explain the chirp. Here's where it gets cool. It turns out, if you have this disk plus magnetar system, the disk size doesn't stay constant with time. Because of the magnetar's gravity, the weakening magnetic field, the accretion through the disk, a bunch of effects, it will shrink. It'll sort of fall in slow motion. And the cool thing is the precession mechanisms, which are the forces that drive the disk around, they change. The strength changes depending on how far away the disk, how big the disk is, its characteristic radius. So as the disk shrinks, the precession frequency, the precession torque gets stronger, it precesses faster, and you get a light curve with a decaying sinusoid. And when you match this to the data, when you try to explain the data, it fits perfectly. The thing that upgrades this from just being it fits to this is something possibly really legit is the chirp is effectively independent of the light curve. The way this mechanism works out, you can measure the properties of the magnetar, especially its magnetic field and spin period, only looking at the spacing between the peaks. Independently, you can measure the magnetar spin period and magnetic field strength by looking at the overall light curve, ignoring the bumps. When you do these two completely separate fits, they give you the exact same magnetar with the same magnetic field strength and spin period. That's more than a coincidence. It's more than circumstantial evidence. That constitutes in our opinion, a smoking gun confirmation, or the best evidence we've had that there really is a magnetar in there. And that has all sorts of exciting consequences. Not only does it prove that it provides the strongest experimental evidence to date that magnetars are born in the heart of these stars, and they are what's powering them, some of them. In some sense, it also has allowed us to watch the birth of a magnetar for the first time. There have been some potentially others, like there have been other ways to potentially observe that we think a magnetar is being born, but this is another, like you're watching a magnetar being born, and that's really always really cool. So it was a really cool discovery. It's always cool, as you know, it's always cool that when you see something in space you've never seen before, right? 15,000 supernovae and there's never been a chirp. And so that's always amazing. Even if our idea is completely wrong, 10 years from now someone figures out something and disproves it, that's fine, right? But that'll always be cool. But then you have this really cool idea that also seems to work, and that's just really fun. It opens a lot of questions, and that's like the best part of science, in my opinion.
No, 100% agree. I love that. Okay, that was really interesting, and I think you're 100% right. And the discovery landscape there is what drives us to do some of this science. It's kind of why we became scientists in the first place, actually.
And my whole like research direction kind of pivoted after that. Like I went from I now I'm going to be, this is what I'll be working on at Berkeley with Dan Kaysen, who
phenomenal.
was the lead author of the original magnetar paper. So
it can also drive you, it can give you your enthusiasm for the next 10 years in case you don't ever have a discovery of that magnitude again. It sort of gives you the energy to keep pushing boundaries.
Honestly, I think even without any discovery like that, I would still just love doing science and being a scientist. I would never expect to have anything like this ever again. Like it's such a wonderful opportunity. Well, it's such a lucky like confluence of events.
Yes, I agree. I mean, it could be a once in a career level event. I hope it isn't, but
Me too. Yeah, I will certainly be working very hard to try and do something like this again.
Of course.
But I also want to acknowledge, like, if that supernova had gone off 6 months later, I
well, you may have missed it.
would have completely missed it. Like,
Yeah.
that happens all the time.
Oh, absolutely.
Yeah.
Are there any downsides to being an astronomer or astrophysicist?
Are there any downsides? Yes. I think there are a few.
All right, let's leave it there.
Number one, I haven't gotten a good night's sleep in like 5 years.
I can verify that.
Self-inflicted in terms of you want to be at night doing things. So
Well, you're also a very hard worker and you don't go to bed at sensible times.
that's true. This is probably what happened regardless of the field.
Probably.
I texted her Happy Father's Day at 2:30 in the morning yesterday.
Yeah, we did have tech. You were up late last night, actually.
Yeah. But that's like a tough thing. Like you do most of your work. You do a lot of your work, depending on the subfield of astronomy, you're in at night.
At night.
And that's tough sometimes. So that's like, I think, a firm downside. The upside that comes with it is you get to look at the night sky a lot. And that's like, I would want to do that anyway.
Oh, yeah, I completely agree.
Another downside is, sometimes makes me epistemically uncomfortable that we're not doing the scientific method in the traditional sense because we're not controlling variables. And this has been thought about a lot. There's a great, I think, paper from the 1960s that laid out this philosophy that you can still do the scientific method. It depends on the independence of the experiments, not of your observations, not like you have to be physically controlling things. And that's why, especially for astronomy, predictions are super important. Mm-hmm. And like I think this idea and a related idea won the Nobel Prize in 2022, something related to this topic or this philosophy. But that's like another downside is, and I don't mean it. The work that astronomers do is amazing, and like the way the field has advanced, I think you can make an argument that astrophysics has had leaps forward more than almost any other field in the last 40 years in physics, whereas a lot of stuff has been kind of stagnant. Astronomy has just been bounding forward. But that's hard sometimes. Like you have an idea and you can't just run an experiment to do it. You have to wait for something to happen again, and who knows if it ever will. Like with the chirping supernova, even though the idea is compelling and the data are really great, that's the number one thing I've heard from people is the data set is very convincing. We have to see more of these, or the idea is not going to really may not hold water.
That's true.
And that's what I'm going to be trying to do during my postdoc is at the Miller Institute is trying to find more of these things and develop out the theory more. But that is scary. Like I don't know if there will ever be another one of these. Not as if we won't catch them. This could have just been a fluke. It could have just been a very bizarre looking.
It could have.
Could have just been a coincidence.
Yep.
And we're dealing with that all the time. Even to the most vetted, thoroughly checked astronomical results, like the first image of a black hole. It could be a black hole, but maybe the Kerr metric is not exactly what we think it is, right? All we could do is a null hypothesis, that's the 10%. We don't know exactly how correct GR is in that instance. Maybe it's not a black hole, maybe it's, I forget exactly what we ruled out. I'm not sure if we ruled out gravastars or boson stars or which one it was. I think we ruled out boson stars, didn't rule out gravastars.
Yeah, I think so.
But there's other exotic things it could be. My money's on black holes.
I think Michael Johnson gave a great talk where he showed the various
shadow sizes and shapes and stuff.
It ruled out a lot of things like that.
It did. It ruled out a ton of stuff, but not everything.
Not everything.
And we can't, without going there to check.
I mean, is that a real downside of being a scientist? Though I think it's part of the privilege of being a scientist that
Oh, yeah.
it's part of the game that you
Yes.
have to go back and prove it again. So it wasn't a fluke, for instance.
Yeah,
Or,
but the fact that you could, like, for example, our theory could be right, but if it never happens again, how will we know?
How would you know?
You don't have this benefit that you have in other sciences of being able to run an experiment, and that's like, that's a. I would say that is a firm downside.
Yeah.
Like as in it's a downside as in if you're in another science, yeah, it's tough. It's tough.
Yeah, it's very funny you say that. I always thought that about exoplanet discovery using gravitational lensing, because you get these caustic crossings that you get these massive magnifications, and you're able to discover these planetary masses.
You're talking about microlensing?
Yes, and so when you get, you basically get these two cosmic alignments. You're never ever going to get it again, at least in our lifetime, for those two objects.
Yeah.
And so while you do detect a planetary mass object through that massive magnification, and you can get independent planetary masses, you actually don't know. You can never measure it again.
Yeah.
And I always felt that limited the microlensing method of exoplanet discovery.
I agree. The one thing is, have you seen microlensing light curves?
I have.
They are so good.
Oh, that's
like
amazing.
Yeah, it's like I'm more worried about that for that. I'm more worried about that for long period planets detected via occultation, because those are really noisy. But a lot of microlensing events. Oh my God, they have some of the most beautiful data sets in astronomy.
Well, partly because you get this massive
The spike, yeah.
magnification. Yeah, that's right. Absolutely. Yeah, interesting. I think for me as well, part of the downside for astronomy per se, but of course it probably happens in a great many other sciences, is sometimes, and we are completely privileged,
Yes.
especially in the Black Hole Initiative and the Event Horizon Telescope, is the funding worries of
we are exceptionally well funded.
We are exceptionally well funded for some good reasons, but some good politics behind
I
the
think it
scenes.
captures people's imaginations.
I agree,
a lot.
100%.
And I love that. I think that. Do you feel that like separates astronomy in particular a little bit from some of the other sciences? While there are practical stuff, I feel like we're like asking these big questions about the universe that otherwise you'd have to go into the depths of like theoretical physics to ask, and they don't have any data. Whereas we are like we're
Right.
There's like an explorer aspect to it, but on some of the biggest questions. And
Yes.
I like that. I think it's a benefit, a strong upside.
I do too, and I think
That's why I'm doing it.
Of course. But astronomers have worked hard, I think, over the years, certainly in the last 20, 30 years, maybe a little bit longer, in try to bring the science of what we do to the general public.
We have great PR.
We have pretty good PR, and especially on things like the Event Horizon Telescope, where we made these amazing images. But also then that we go into schools and we do education, and a lot of other sciences do too, but we have fancy graphics and real, just absolute gems that go with it.
Yes, the visualization
The
aspect.
visualization is amazing. No, I completely agree. Absolutely fascinating. Absolutely fascinating. Okay, well, we should probably hurry up a tiny bit because we've been doing this about 3 or 4 days. What would you tell your younger self starting out on this journey? Now, bearing in mind you're only about 305 now. I mean, you're a fairly young chap. You're a fairly junior scientist in terms of your career length.
Yes, and by younger self, what do you mean? Like what? Like when I first met you, or like when I was in middle school?
Yeah, given that your career is
That was about 5 years ago.
Yeah, fairly young, so it's a nascent career, I would say. Yeah, but maybe starting out in the Event Horizon Telescope, what do you think you've learned on how to be a scientist in the past 5-6 years? I may have my own answer for this, by the way, for you in particular.
Yeah. This is a tough one.
It's a hard one.
It's a tough one because, I mean, what would your answer be?
I think my answer would be to have patience and to let the science come to you. I think often you chased it because you were so eager, and you're still eager, of course, but you were so sort of green and wet behind the ears, you chased it. Not necessarily too much, but I think you didn't allow the science to come to you.
I very much agree with that. And I was trying to formulate something similar. I was just, I was very aggressive about trying to prove myself.
Yes.
And
we always knew you were talented, by the way.
I appreciate that. It certainly didn't feel like that from my perspective. Not that anybody was mean to me or anything, but like I was I felt like I had to prove that I deserved to be here. And some of that was the honor of being and privilege of being the only undergrad who's formally involved in HG,
You were the only
which is an extraordinary privilege, and I'm grateful to everyone who was involved with helping make that happen. That's a lot of pressure.
It is, but I would turn it around by saying the fact you were there
is my fault.
well, no, but you were there on merit. So if you weren't good enough, you wouldn't have been there. So I think not that you didn't have enough confidence in yourself. I think you did, because you're a very talented guy. I think you were so busy trying to tell us how much you were worth being in it. We knew that. It's hard though, because in your defense, you were very young. And
I just want to give some context. When I joined the HT, I was 18 years old. 18? So it's
and you were an undergrad.
Yes, first year undergrad.
First year, and you were rubbing shoulders with Jim Moran, who'd been in
who invented VLBI.
And you've been a scientist for knocking on the door 50 years.
And you're not exactly the most you and people and a lot of other people like Michael, and it's very intimidating. You guys have storied careers and are like incredibly smart, and I look at you guys and I'm like, I want to be like that, and I want to be like that now. And I was the mistake, really, was I gave myself no time to mature or evolve into anything like that. I just tried to approximate what I saw as your success as best as I could, and
but I think what you'll find, and this is sort of my me being 500 million years old, is that you have the intellect, and you're a very intelligent guy, and you can code up the zoo, and you know the science inside out. But I think to become a good scientist, and I learned this the hard way actually, and I was similar to you, is I think takes time.
Mm-hmm. Things have to marinate. You can't rush it.
They have to marinate sometimes, and you have to also then be willing to know when some ideas need dropping, and some ideas are worthy, and what type of data are going to fit, and that kind of judgment takes time. And I don't think it's the sort of thing you can learn overnight.
Yeah, you can't speed it up. It just takes time and experience, and I didn't have that, and I still don't. I have it more, but I don't have it to the level that I still have a lot of growing to do.
Possibly intellectually, I'm not sure you do. But you're very.
I have so much more to learn.
Incredibly clever. But
Thank you. I have so much more to learn.
But to be a good scientist, and you are a very good scientist. But to be an elite level scientist, I think you can't do in the 8 years you've been a scientist.
Yeah.
Some of the best scientists we've ever known, typically, not always, but typically have decades of experience. You get these exceptional level people who do unbelievable things in a fairly short period of time, like the Marie Curies, who unfortunately she died early. But that's a relatively rare person that does that.
Yeah, I agree. It's something I didn't. I agree with you very strongly. It's something I'm still working on, I made a series of postdoc resolutions, what things I want to do better in my postdoc that I did in my PhD, and they're largely centered around that, taking the time to better understand the literature of the field I'm in, the underlying theory, and in particular, something I wrote down. I literally wrote this down. I want to be respected for my insight and not just my production, which is something that I struggle with. I for a long time I equated producing something quickly with the positive feedback I got from producing things quickly with successful science, and what that led me to do was to stay in certain comfort zones where I could work quickly.
Yeah,
and I want to be better than that. I would like to be the kind of person that people talk to because of the ideas they have, and not just because they can do things quickly, which is not what I've not achieved that yet.
No, it takes time.
Yeah, it does. Yeah.
I think it's one of those classics of, and I've quoted this for a long time, it's actually in Star Wars at some level as well, is I think there's a huge difference between knowledge and wisdom.
Yes.
And knowledge you can gain quite easily. Wisdom can take decades sometimes. Again, unless you're one of those very, very, very rare people who...
We know you're talking about yourself, David. It's okay. You can come say it out.
Not at all.
You see those gray hairs?
Yeah.
That's the wisdom right there.
I earn these grey hairs. That's through my
Silver
children,
fox.
But, that's right. But it's a tough thing to, as you say, especially in the world we're in, where we are driven by results.
Yeah, it's the publisher perish is real.
Publisher perish, and you know, you and I have delved into this on Astroveo. You know, a good AI, a good LLM AI model can probably reproduce a lot of astronomical knowledge.
Yeah,
but
we have a video coming out that may dispute that.
Yes, we do. Well, no, the knowledge it can learn, and the mathematics and the coding, but the insight from those.
Oh yeah,
teachings.
I'm saying we have a video coming out that will dispute that.
Oh yeah, absolutely.
but I do get your point. Yeah, it can regurgitate things that you completely incapable of doing an analysis
without all the understanding of.
Yes,
and so that's
what's important and
what's important. And, yeah.
But that's fun. I mean, taking it back full circle. That's why I struggle with the question, because I don't know what I could tell my younger self that would convince him. Because if you look back, the things I did were technically. The way I worked and like the approach I took. If you were trying to optimize for something, that was technically the best approach. Stick in your comfort zone, do what you do best, what you're good at, and leverage that to try and crawl your way up. And that worked, but it didn't help me grow. And I think that was the issue. But I don't know. I don't know if I could. I don't know what words I would say to my younger self to say, you should be trying to grow and not just trying to, you should be trying to grow yourself and not your CV.
It's tough though. It is. It's very tough. Yeah, I think we've answered that really well. But it is. It's very tough. It's also. It's just tough when you're younger, because I think you also, and you've done it, you're getting better, but you're the sort of person, and I think I was the same, and I suppose I'm still somewhat similar, I'm trying to be better, is you put in awfully long hours. And so I think a lot of your success was driven by just sheer
volume.
And just very, very long hours. So volume of work and pushing yourself to the very limit. And that's a young person's game, because as you get older, you can't do it. And not just physically, you may have a family, you may have a spouse, you may have financial obligations to do something else. You may not be in the best of health. So I think it's a young person's game that you can get away with. And as you get older, that will just not be you just won't be able to do 18-hour days anymore. Yeah. And you and I have had this discussion several times. I still personally think you work a bit too hard. But, and also just take time to smell the roses and go and do things with your wife, and just like, there's more to astrophysics as well, by the way.
Yeah, I know. And something that occurred to me very recently is I've been so obsessed with, I really love what I do. I want to do it forever. And I've been so obsessed with trying to figure out how to optimize so that I can do it forever, that I'm forgetting to enjoy that I'm doing it right now.
You're already doing it.
Already doing it. Like,
right, yeah.
And the funny thing is, the part that I enjoy is not necessarily the part that I'm going to even have the most time for, even if I do succeed and get a faculty position or something, like, because I like the science aspect. But as a professor, you spend more time working with students, writing grants, that sort of thing. You're doing a lot less of like the coding and the paper writing. And so it's like this ironic, it's like this irony that I may spend there's an idiom I'm trying to think of where you spend so much time trying to like make something last that you forget to enjoy it while it's here.
No, I know what you mean.
Yeah,
I can't remember the idiom, but I do exactly what you mean.
Yeah.
Or take time to smell the roses.
Yeah.
You know what I always struggled with when I was younger and an up-and-coming scientist?
Just being so handsome.
Well, never struggled with that. I was always really good at observing. I understood telescopes really well for some reason. I understood the night sky really well, and I could write a good enough proposal to get the telescope time. And I wasn't the world's best coder, but I always found a way to do the data reduction. And I could look at a spectrum and see lithium and see H alpha and see binary stars. So I always had that skill. I was really good at identifying patterns, actually. Without a computer, I just have that. I don't know why I have it, but I have it. But I always worried that as a scientist, I wouldn't be able to come up with enough ideas to be viable. Like I was always relying on either my supervisor or somebody else or being in a collaboration. And then I realized one day that the very fact I was getting a lot of telescope time and I was being part of these collaborations, I realized that I was actually essentially the ideas person. And in fact, I was having too many ideas. I wanted to do this and I wanted to do that, and what happens if this happens, or why is that star doing that, or why is this open cluster doing such and such? And it became a bit of a problem where I almost was unfocused because I was almost having like too many good ideas. And it became a bit of a problem. It's like, no, okay, you've had a couple of ideas about this open cluster, about stellar evolution, concentrate on that, write a proposal, take the data, write the paper and so on. And so that was a lesson I had to learn like the hard way when I realized I wasn't completing projects as often as I probably should have. But it was also that reason the reasoning of I want to be known as someone who can come up with ideas.
It's like you are that person.
Oh yeah, I'm already doing it. Damn it! Why didn't I think of that?
That scares me, honestly. I have some confidence that if I have a deficiency that I can recognize, I know I'm willing to work really hard to try to fix it and be better. And I earnestly believe that, and that's like but if I can't recognize my own deficiencies, then that becomes astronomically harder, no pun intended. So that scares me, honestly. The idea that I might be focusing on entirely the wrong things to improve on.
Well, that's where I think you need time away from the office occasionally to go for a walk with Astro Puppy and your wife, or go, take a walk in the forest and just get away from the science occasionally, just to reflect on your part in the game. And that can be very insightful where you think, oh, maybe I am doing such and such, excuse me, incorrectly, or not as well as I could, or I'm focusing on too much on this. I think time away sometimes helps one see the role you play in science.
I like that. I'm going to do my best to make that happen. As we've discussed, I'm trying to move a little bit away from the more unhealthy way I was working in grad school to try to be more sustainable in my postdoc. So I'm going to try really hard to incorporate that.
You did a lot of hours in grad school, that's for sure.
Entirely self-inflicted, but
well, no, there's a lot of pressure, and you were wearing many hats in your defense. But it's. Okay, well, that was a really interesting discussion there, Mr. Joseph. Thank you.
Dr. Joseph now.
Oh, with Dr. Joseph.
Yes.
Well, we talked about this earlier. Of course, my children call you Mr. Joseph. I'm so used to it. You are indeed Dr. Joseph.
I've been Mr. for so long. I've only been doctored for a few weeks. It's okay.
That's true. That's true. Has the degree been conferred yet?
It has. I requested a rush conferral so I could come start this job. But I haven't received my dissertation in the mail yet. I'm really excited for that.
Oh.
They're going to print it out, It's going to be a tome.
It is a tome. Yeah, you wrote a very substantial piece of work.
I could stand to write less.
You could have made it more trim, that's for sure. It was voluminous towards the end. Well, okay, we should think about wrapping it up. I think this has been a fabulously interesting experience.
Very awesome conversation.
I know. So we definitely can't do the coast to coast anymore because we're on the same coast.
Yes, it's just coast.
That was quite good, yeah.
Thank you.
Coast up.
It's about the delivery.
I know, she was just like, it just rolled off the tongue. That was pretty nice. Well, I'm really excited to have you here for the summer.
Me too.
Working here at the BHI, the Black Hole.
I'm just excited to hang out with you.
I know. In between, just so you know, in between some of the editing, we played a game of chess, and I got
He did great. He did amazing.
Well, first ever draw, because you always win.
That was a great game.
That was a fun game, actually.
He found an excellent draw right at the end.
Well, but it feels somewhat nihilist, because you could back and forth. It's like,
No, you did awesome.
Yeah, I actually think you were going easy on me, actually.
No. He's I love it. I really love playing.
Yeah, I'm going to start reading down how to play, because you're so much better than me. And then you showed me a picture. You were playing in the womb. It's like, come on. How old were you in that picture? 3?
3, yeah.
Oh, jeez, I can't compete with that.
I was wasting time playing in the womb instead of investing in NVIDIA.
I know, yeah. Or Apple or something.
Yeah. This is not financial advice.
Please consult your company for financial advice. Or is it, what do those adverts say? Shares can go up as well as down.
Yes, yeah.
Well, so welcome back home. Welcome back to Boston.
You. I can't wait, yeah.
You're going to do some great science this year, or you already
Thanks,
are. I'm
Thanks,
really
man.
looking forward to the next steps, and we'll talk magnetars and equations of states of neutron
Yes.
stars. And
We have unfinished business.
Yes, we do, and much more chess to play.
Yes.
It has been a thorough pleasure.
You too.
Thank
Thanks
you.
so much,
I
man.
love you, brother. I love you too. We
jinxed that, yeah.
We did.
That's on camera.
Hey,
That was not planned.
no, that was completely par hasard, as the French would say.
Right.
So, well, lovely. We'll see you next time, Jacob. Jacob.
No!
I haven't done
We
that for
have
ages.
video proof.
Oh, I've done it so many
Sometimes
times.
he calls me Jacob. I have no idea why. We have known each other for almost a decade.
Yeah, well, I'll tell you why exactly. So I work at Applied Materials, and I'm a program manager, and I have a teaching lab, and my instructor is called Jacob.
Oh.
And I call him Joseph all the time. And he's such a nice guy. He's like, oh, no, don't worry. I like, no, I keep doing it. And occasionally he's like, oh, my name is Jacob. And with you, sometimes I call you Jacob. I need a different set of
Yes,
names.
he'll have to change his name.
He can change
I
his.
think. Yeah.
Actually,
Sorry,
he can-
Jacob. Or is that, should I even call you that?
I know, well,
Sorry, Joseph.
Joseph too. Yeah, Joseph Applied Joseph. There you go.
Oh, yes.
Anyway, this has been super duper. This will be one of the flagship videos, I think, for Meet the Astronomers.
No. That Professor Kane was amazing.
Yeah, he was brilliant.
And Burchin was
phenomenal.
remarkable. This doesn't even crack top 5. And we only have like 6.
So basically, you're sick.
Yeah.
So anyway, thank you for joining us. This has been another episode of Meet the Astronomers. We'll see you again another time. Any comments or questions, please leave them for us and we'll get back to you.